Programming the Arduino I/O Part 2 Input. I'm your host, Louis Laughlin. In this video, we will continue our exploration of how to program and use the Arduino input-output. Our main emphasis here will be detecting switch closures. Again, the Arduino, pictured on the upper left, is a 28-pin RISC microcontroller operating at 16 megahertz. It can do any number of control functions. Our major focus in this video will be the digital I/O pins. In part 1, we learned how to program the output and why electrically things operate the way they do. In this video, we're going to be looking at input. Alright, here's the schematic that we used in part 1, same one we're going to use in part 2. Up here is our reset and our reset pull-up resistor, our 16 megahertz crystal. We need to focus on the two switches connected to digital pin 7 and digital pin 8, also known as SW1 and SW2. We will also be using in this the two LEDs from the first video that are connected to digital pins 9 and 10. We're not concerned with the 10K pot up here. That's for the next two videos when we start combining all of this together. Alright, once again, when a microcontroller like Arduino, or about any other really, is first powered up, all of the switches are open. Again, I'm using a simplified switch diagram to explain what really goes on behind the little electrical pin you connect your switches and LEDs to. If you connect a voltmeter between ground and the pin, before we set up the pin states, you will read nothing. It's just an open connection because that's really what it is. All digital circuits are simply a group of switches. The switches might be transistors or MOSFETs, but broadly they're still switches. Alright, once again, we're going to go to our setup section of our program, and we're going to use once again a command called pin mode, and we're going to take a pin and program it for an input. If you notice the switch diagrams here, I closed switch 3. Again, look back at the previous slide. Before we did the command, switch 3 was open. In this case, switch 3 is closed. So here is your input logic. This is sort of a high impedance. And in this state, if we tried reading the pin to find out if it's high or low, we're going to get an inconclusive return. It's just sitting there floating. All you're going to be reading is static and noise. In this condition, the pin is useless. Now, if we connect a switch to the pin as it exists, we have to use what is called a pull-up resistor. In this case, we have a switch connected to ground like we saw in the original diagram a few frames back. But I have to have this 10K resistor with the switch before I connect it to the input pin. What this simply means, as long as the switch is open, I've got 5 volts on the pin, which when I read the pin will return a digital 1. Digital 1 being 5 volts, digital 0 being 0 volts. When I press the switch, the voltage to the input pin will go to 0 because the voltage will be dropped across the pull-up resistor and the input pin will be switched to ground through the switch. And we'll return a 0 when we read the pin. That's how we knew the switch would be pressed. Here are a couple of other configurations for hooking external resistors to switches that connect to microcontroller pins. On the left is pretty much the pull-up resistor again. The 1K resistor between here's where the switch and the pull-up connect is probably a good idea. I use 220 ohms. A lot of times I don't use 1K. Others use 1000 ohms or 1K. I use about 220. So does parallax. Nonetheless, what this means, if you have the resistor here connected to the pin and you misprogram the pin to say an output and you output 5 volts and you press the switch, you're going to blow the pin because you're going to short an output right to ground. So putting in this resistor will protect your pin if you misprogram it. On the right, we have what is called a pull down. This time the switch is connected between the 5 volts and the resistor that goes to the pin. Again, this is to protect the microcontroller pin. And of course, this 10K going to ground means it's going to read low. As long as the switch is open, it's going to read low or 0. Why do I need that resistor there? Well, what if I program the pin for low and I switch it to low through the microcontroller? Without that resistor, if I press that switch and it's programmed for low, it's a short circuit to ground and I'll damage the microcontroller. So it's a good idea to use these input resistors between the switches and their pull-up or pull-down resistors in case you misprogram the microcontroller and you'll damage it, and that's the end of it. You'll have to replace the chip. All right, let's look at this here, going back to my switch diagram. Now we're going to go in the setup routine again, and once again, here is my pin mode switch pin input. Again, I closed SW3 to connect the pin electrically to the input logic. But now what have I done here? I'm using the command digital write SW pin high. What this has done, it has closed SW4. R1 is actually inside the microcontroller. Everything in here is it has the Arduino pins, its digital I/O pins have internal pull-ups. By using the internal pull-ups, I don't need external pull-up resistors and all of that on the pin on the outside. I can simply connect a switch to ground. It will probably still be good idea to connect a 220 ohm resistor in here between the switch and the electrical pin, because you could always still program it as an output trying to output 5 volts, and if you push the switch you'll short it to ground and blow the pin. But this is how you use an internal pull-up, is with the digital write SW pin high when the pin is in the input mode. Again, going back to our original diagram, here's a blow-up of it in the corner. These two commands up here, pin mode and digital write, means that I have taken digital pin 7 and digital pin 8 and programmed them to be inputs. And I have activated the internal pull-up resistors. In the present state, if I put a voltmeter from here to ground or here to ground, I'm going to read 5 volts. When I press the switch on either one, it will go to 0 volts. Again, if I put a voltmeter with these internal pull-ups activated, you'll read 5 volts here, and you'll read 5 volts there. If you press a switch while you're holding it, the voltmeter on there, it will go to 0 volts. So the state of the pin now is going to be 5 volts as long as the switch is open and it's programmed as an input. Here's a picture of some push button switches. These are, I assume, normally open. Push button switches come in 2 types. Normally open, that is, you press the switch to make a contact, or normally closed, you press the switch to break the contact. These, for instance, are used in PC boards. They're used in the front panels. If you take the front panel and the circuit board off of, say, a VCR and look down on the circuit board, these are what you're going to see. These are more panel mount push button switches that you'll see on various forms of electrical equipment. Again, they can be normally opened or normally closed. Again, going back to our diagram several frames ago, not only do we have 2 switches connected, but for this program we're going to explore next, I have 2 LEDs connected in what is called the source configuration. Go back to video 1. That is, if I have a high, that if I program this either digital pin 9 or digital pin high, it's going to output 5 volts on the appropriate pin and the LED will light up. Again, notice pin mode on each of these is for output, and I set them up with digital right, LED, whichever, low to make sure they're off. This would have been put in the setup statement. Alright, quick review of your general programming Arduino. You usually have a comment section at the top to fill in the user and yourself later on, what is this program about. This is your setup loop. This is just a setup, it's not a loop. Setup is operated on only once. This is where you set the I/O pin to whether you want it to be an input or an output and initialize its level. Loop will repeat endlessly. That is where your main program is going to go. Alright, here's a picture of the Arduino IDE, Integrated Development Environment, as I think as they call it. Let's look at what we have here. Define SW17. That is, anywhere that I use the term SW1 for switch 1, remember I had it connected to digital pin 7. That has a normally open push button switch connected to ground. And I'm LED1 9. That is, anywhere that I put in LED1, the compiler here will know it's digital pin 9. Digital pin 9 is where I had an LED connected. In our setup statement, pin mode SW1 input, okay, that's for the switch. That sets it up as an input. Digital write SW1 high. Remember, anywhere where you see SW1, the compiler knows it's digital pin 7. In this case, our digital write SW1 high turns on the internal pull-up resistor. What this means is unless I press the switch, if I read that pin, it will come back high or digital 1. Pin mode LED 1 output. That's where I connected the single LED. Now we come down here to the loop statement. This is the one that will repeat endlessly. Here I've chosen a variable, a byte type variable. A lot of people like to use integer. I use byte. An integer chews up 2 bytes of your static RAM. Byte uses only 1 byte of your static RAM. and it's a variable I call pin state. It's just a variable. It's going to come back 1 or 0. When I do the command digital read SW1, what it does is that it will find what is the electrical state on SW1. Now, as it was set up before, it will return a 1. Because remember, if the switch was open, the pull-up would maintain it at 5 volts. And this command here, you will return a digital 1. Then I'm going to use the term digital write LED1 switch state. Okay, I'm going to transfer whatever the switch state is to LED1. If the switch state is 1 or high, the LED will light up. Here is a little bit more of a blow up on it, but a slightly bit of different. It's a little bit different. The one on the, you really don't need this command down here, digital write LED1 low. You can put it in there if you want to. It's not needed. The rest of it is the same. I used, instead of pin state, I used the variable I, but all of it is exactly the same. All right, this is a little different. Oh, let's go back to the previous frame. Again, byte I equals digital read SW1, digital write LED1 with whatever I happens to be. Of course, with the switch open, that is, you're not pressing it, the LED will be on. If you push the switch, the input as it loops around when byte I equals digital read SW1, when you push the switch, it will return a 0 or a digital low, at which time the digital write LED1 with I, it will be writing a 0 to the pin and the LED will go off. In other words, push the switch, LED goes off. This is a little bit different. Everything is the same, but you notice one difference. You see the exclamation point. Okay, in the Arduino IDE, an exclamation point is a not function. So if digital read SW1, for example, returns 1, the not function will reverse it. Again, the not function will reverse the state of whatever it's being used at. So if digital read SW1 returns a high, which it will if the switch is not pressed, that high is changed to a low by the exclamation point, the not function. And so I will be low, and in this condition, digital write LED1I, the LED will be off. When you press the switch, the LED will come on. Why? You press the switch, it goes to ground, the electrical potential at the pin is 0 volts now. 0 volt is a digital 0 or low. Digital read SW1 returns a low. The not function will take the opposite of a low, change it to a high, and digital write LED1 high turns on the LED. So press the switch, LED1 comes on. That's simple. All right, just like you could always, of course, again, connect other things to an Arduino output pin besides just LEDs. Note that an output pin has a maximum current of 20 milliamps. Don't hook up 12 pins at one time trying to source or sync 20 milliamps. Not a good idea. Again, In this case, if you use the statement where you press the switch and the LED comes on, you could connect this in for the LED, press the switch, and the relay comes on. Same thing here again, of course, press the switch, you get a high output on the output pin, in that case digital pin 9 EI LED 1, and you can cut on a light. And so that's all for part 2 on output. So part 1 we studied how to set up for input. Part 2 we looked at how to set up for output. Excuse me, let me reverse that. Part 1 was output. Part 2 we just did was input. Part 3 we're going to be looking at analog to digital conversion. For more on all kinds of electronic topics and circuits, visit my website at www.bristolwatch.com. Thanks for visiting.